Welcome everyone to the next Gen 4 International Forum webinar presentation. Today's topic is on safe and final disposal of spent nuclear fuel in Finland. Our presenters are Mr. Mika Pohjonen and Ms. Sanna Mustonen. Doing the introduction today is Dr. Patricia Potier. Patricia is the group leader of the Radiological Materials Group at Pacific Northwest National Laboratory. She's the National Technical Director of the Molten Salt Reactor Program for the U.S. Department of Energy. She's also the chair of the Gen 4 International Forum Education and Training Working Group. Patricia.
Good morning, good afternoon, good evening, everyone. I hope you don't have so much snow like we have right now. Unbelievable. So it's my pleasure to have today Mr. Mika Pohjonen and Mrs. Sanna Mustonen, who are going to present this webinar. Mr. Mika Pohjonen is the Managing Director of Posiva Solutions. He has over 30 years of international experience in the energy sector. He has previously held various sales and management positions in the engineering and management consulting business. Mr. Pohjonen has a broad experience in the nuclear energy business, acquired in numerous projects in Finland and most European countries that utilize nuclear energy, as well as in the Middle East and China. He has also worked as an invited expert for the International Atomic Energy Agency in environmental and social impact assessment. Mrs. Sanna Mustonen, Safeguards Officer of Posiva, has 20 years of experience in Posiva and Posiva Solutions. During her career in the program for geological disposal of spent nuclear fuel in Finland, Mrs. Mustonen has worked in versatile projects concerning safeguards, data management, excavation works, and machine development, among other things. She has been acting in Posiva's safeguards tasks since 2018. Prior to working in Posiva, Mrs. Mustonen has worked in mining and in exploration companies. So without any further delay, I give you the floor. Mika, thank you very much, both of you, for volunteering to give this webinar. Thank you.
Thank you, Patricia. I hope somebody lets me know if my presentation doesn't show. If it shows, I start. So my name is Mika Pohjonen. I'm from Posiva Solutions, and I'm very pleased to have this opportunity to tell you a few words about our spent fuel geological disposal project in Finland. Okay, so a few words about Posiva, the utility which is responsible, or company which is responsible for safe and cost-efficient final disposal of spent nuclear fuel of its owners. Posiva is a private company which is owned by two Finnish nuclear utilities. The Oulusuuden Voima is purely privately owned, and then Fortum is stock-listed company. We have approximately 90 employees at the moment, and we hire something like 100 expert person years per year, and as we are now in the middle of intensive construction period, we have contractors, 150 contractors, workers on site. Our turnover, which is a nice name for a cost, was 127 million, because we are cost to our owners, and the subsidiary Posiva Solutions has been established in 2016, and that sells expertise, our accumulated expertise, and has had projects in approximately 15 countries during this time. I show you a photo of our home island, which is in southwestern Finland, approximately 300 kilometers from Helsinki. It's a 5 times 1 kilometer island called Olkiluoto, and in the middle, in the top, you see 3 nuclear units. In the middle, Olkiluoto 1, then the second box-like one is Olkiluoto 2, and then Olkiluoto 3, which is now in commissioning phase. And then left of those power plants, you see our wet storage was for spent fuel. All the spent fuel produced on the island since 1979, when the first unit was commissioned, has been so far stored in this wet storage. In the upper right corner, you see a site or place for our repository, final repository for operational waste. It's low and intermediate active waste, and the repository has been in operation since 1992. We also have their space reservation for decommissioning waste, but even the two older units have now 20 years more operating time, so they will operate till 2044 at least, and the new unit will operate from 60 to 80 years. In the forefront, you see the topic of the day, our construction site of final disposal facility called Onkalo. The construction is ongoing. It was started in 2016, and the application for operating license was submitted in the end of 2021. This is our project in copper shell, not in a nutshell, because we use copper canister. From the left, first 20 years approximately was spent for site investigation, site selection, and concept development. We applied for our first and most important license, which is the only one which needs to have a political approval. It's called decision in principle. We applied for that in 1999 and got it in 2001. After that, we had secured the site. We could start constructing Onkalo, which has a dual role. It has been serving, and it serves as a research facility, but it also will be a part of the final disposal facility. So it's not a separate laboratory. In 2012, after approximately 10 years further development, we were ready to apply for a construction license, and we were granted that in 2015. And then we started constructing of the final disposal facility itself. The intensive construction started in 2019 when our owners decided that we go forward, and we built really the encapsulation plant, etc. So since 2019, our building construction activity has been quite intense. And I already mentioned that we submitted in this a little bit more than 1 year ago, we submitted the operating license application. Based on our experience, we estimate that it will be, the handling of it will take approximately 3 years. Of course, it's not in our hand, it's in authorities' hands. But if we get the permit or the license in 2025, we are ready to start the operations then, and we will continue approximately 100 years. This is not because we would be especially slow, but this is because Olkiluoto 3 will produce electricity at least 60, if not 80 years from now. Our concept, in short, is that we pack the fuel assemblies to cast iron insert, which is then placed in copper overpack, and then that canister is lowered to depth of 420 meters, put in the final disposal holes in the tunnels, and surrounded with bentonite buffer. Then the tunnels will be backfilled with bentonite and closed with concrete plug. And the bedrock there, 420 meters above us, is 1,900 million years old, so it's very stable. We are in the middle of a tectonic plate, so we don't have especially strong earthquakes, only magnitude 1 to 2 as a result of glacial rebounds. So it's a very, very stable rock environment. As I mentioned, we have used Onkalo, which can be seen here as a graph on the right side. We have been using that for hundreds and hundreds of different studies and investigations of bedrock, of rock construction, and different tests and demonstrations. And we do have dozens of test holes from the surface and underground, 58 deep holes from the surface in the area. So Onkalo has been designed to be part of the final disposal facility, as I mentioned. The benefit from this is, of course, saving cost, not having an extra laboratory, but also getting the information of the environment from the real site from the very beginning. This is how our facility will look after 100 years. It's quite small, 2 square kilometer footprint only. And this is, of course, due that we have a relatively small inventory in Finland, 5 reactors only, and we need to dispose of 6,500 tons of uranium, which is 3,250 canisters. I show you a few photos of the project status above ground, and at the same time I will take the pointer here. So here is a picture of the encapsulation plant construction site almost 2 years ago. I show you this picture because we can then see inside the plant. Here is the reception hall where the transfer cask is coming, and then it will be lifted in the vertical position and lowered into a corridor which is under this whole building. And along the corridor, it will be transported under the hot cell, which we see here, the place where all the magic happens, when the fuel will be taken out of the transport cask. It will be dried and it will be placed into the copper or the cast iron inset, which is already in the copper canister in this phase. Then the canister will continue its travel. These we don't see anymore, but there's a welding station, there's a machining station, and then there is an cleaning and inspection station. And this area here is the place for the shaft where the elevator will be lowering the cask or the canister down to the depth of 420 meters. And here the same is, that was from left to right, this is from right to left. In fact, the same processes. And here you see the shaft as the last phase of this process. Just today we have launched in YouTube a very nice animation of this process. You can see that by searching for Posiva encapsulation plant in YouTube. So that is in detail describing the process which happens here. This is the encapsulation plant 8 months ago. Approximately 8 months ago, the building was completed and the installations of equipment and machinery are ongoing. These are a few pictures or photos from inside. The message of this slide is mainly that if you follow us in Posiva Solutions and Posiva in YouTube and LinkedIn, you find a lot of information, almost of everything we do. And as I mentioned, there is this animation released today, and then there is a quite recent animation of the whole process as well in YouTube. So if we then dive underground, here we do see the first final disposal tunnels in the graph. Here they are these which have been marked with green and still yellow. This was an old picture. These were all now green, meaning completed in last summer. And then you can see the driving ramp down where we have different research and development niches. And then you can see 4 shafts. And here are the technical facilities where the next picture is probably of the shafts, and then there are these technical facilities. And then in a light color, there are future tunnels. We will only excavate 5 tunnels at a time, and then we will fill them with canisters and bentonite, and then during that we will excavate the next 5, etc. here we have some photos of the shafts in the different construction phases. We have personal shaft, canister shaft, and then 2 shafts for ventilation. All the operations will happen via the shafts. The ramp will be used only if we need to bring some bigger machine or something up from the repository. But to avoid that, we do have good technical facilities for maintenance, repair, parking. We have cafeteria there and facilities for employees, etc. So this is just the development in the upper left corner. It's from September 20, and here it's December 21. So everything there, including the ventilation, electricity, etc., everything has been finalized. Okay, now there's again some delay in changing the slide. Yeah, good. So the spent fuel transport is relatively simple in our case because most of the fuel we have is in Olkiluoto. We have 3 reactors there. And the other power company, Fortum, has 2 reactors in Loviisa, in southern coast of Finland. It's approximately 300 kilometers away. And this fuel will be transported either by road or by sea. It has not been decided yet, but in the standard transport casks. As I mentioned, we submitted the world's first operating license application in the end of 21, and it is a 17,000 pages e-document. So it's a series of documents which are all cross-referenced, and to make the studying of those easier for the authorities and stakeholders. It also contains, of course, the first safety case in the world for operating and post-closure safety, which has been submitted to authorities. And we kept our schedule again, which was loosely defined or defined 40 years ago. We expect that the H2, half 2 of 24 would be the earliest time we could get the permit, but might be 24, 25. As I said, it is not in our hands. I want to mention that in the beginning of next year, we will start a trial run of final disposal. And that is, in short, final disposal, full final disposal operation. The only difference being that we use mock fuel, but mock fuel elements are like real fuel elements by dimensions and by weight, etc. So they are not only they are radiating. That's the only thing that is missing. Otherwise, we will implement fuel transport, the whole encapsulation process for 4 canisters, final disposal to the special tunnel which has been excavated for this purpose. It's here. Trial run tunnel, and then we also will try the reverse action of the process, because we will retrieve a damaged canister along the canister lift, or hoist the canister up to the encapsulation plant and cut it open, take care of the waste, and return the waste or the nuclear fuel to such a state that it can be packed in the new undamaged canister. And this is open against a fee for other waste management organizations if they want to participate and learn how we ended up in this result and what we would have done differently, really to learn what is behind this 40-year projects. This is not only technical test. All the equipment and machinery have been tested and approved before this, and of course here they function together as a process. But in addition to technology, we also test all the methods and procedures and organization, which then will take care of the final disposal starting next year. So we do have a production or operation organization already in place since 2020. And they are acquiring the operation of the plant in the start of this trial run, and that will be, of course, also very interesting to see how well the plants are functioning in real life. Again, some delay. A few words of the public acceptance of our project is that from the very beginning of our company's owners operations in 1978-79, we have been very open and transparent. And the #1 rule has been that everyone is an important stakeholder. We have identified the stakeholder, and we are very proactively and very fact-based way we are communicating with them. And it's to be noted that it's our responsibility to be understandable. So this is the second cornerstone of this communication strategy, that we need to be understandable. So we cannot send scientific reports to school children or media is not interested in them, etc. So we have to design our message in such a form that the stakeholder in question gets the information he or she wants and understands it. More than 20 years ago, in the decision in principle process, our home municipality called Eurajoki had the opportunity stipulated in the Finnish law, where every municipality where a nuclear facility is proposed has a veto right in the decision in principle process. And the veto right is permanent. So if one council says no, then it is committed. It is binding to the next municipality councils as well. And yes is permanent as well. So it cannot be overruled by the later councils. And the vote was 20 yes, 7 no. And as I mentioned, this next step of this decision, or the last step of this phase, is that the decision for ratification to the parliament, and then parliament it was ratified by votes 159 yes and 3 no, and 37 members of parliament were up. So it was quite an process. And the main arguments behind the decision of the parliament were that aiming at final disposal is a better solution than just resorting to interim storing. If you look at what happens in Europe now, or what has happened during the last 400 years, you see that it's not very stable in the long term, or in the short term. In the long term, meaning tens of thousands of years, we will have ice ages, we will have hundreds of meters of water on top of the repository area, so interim storing does not come into question. And option for retrievability of waste canisters must be maintained, and this is what we do. And also the moral justification is the present generation, or that generation, previous generation, which built the nuclear power plants, has to accept the responsibility for nuclear waste as well. I would say that we have had 3 shafts to success if public acceptability is concerned. I say shafts because we go downwards, not pillars. So the first is trust and transparency. As we all know, it takes years to earn the trust, or a long time, and only minutes to lose it. And the trust we have earned from our stakeholders is our most valuable asset. We do not risk it under any circumstances. We can risk money, but we don't risk the trust we have earned. Then in Finland, it's the authority is not only nuclear regulatory authority, but also the other authorities involved are independent, and they are trusted by people. They are also quite active in their communications. They are interactive. So if people ask something, or stakeholder asks something, they get the answer. Then the process is different. Various permit processes are clear. Responsibilities and roles as well, so stakeholders know when they can affect a certain process. And then a third shaft, I would say that we have a very small community around us, 50,000 people only, and that's so small that during 40 years plus, everybody knows everybody knows somebody who has worked in our power plant or our repository project, or they have worked there themselves. And these people who have worked for us, who are working for us, are our most important ambassadors. So if they go home and say that they don't trust, or things are not taken care of well, then our trust would be ruined. Our communications could not save our trust. But they obviously have gone home for 40 years and to their friends and telling that things are taken care of responsibly and well on the island. And of course, we are also not only employing and transparent, but also we of course pay taxes locally in the Finnish system. We pay taxes to the municipality quite, no, I cannot say a lot. And as I mentioned, we have been transparent, but also very reliable. So our reactors, as a result of intensive maintenance and very well planned operations and maintenance, we have raised their output electricity effect from 660 to 900 megawatts, and we have been always in the top 4 or top 5 of world's reactors in terms of availability. So what we would like to say that we are proud that we do have a solution for the final disposal of spent fuel, and doing that we have a significant role in climate protection, as we have solved the last big issue in producing carbon-free nuclear energy. And those were the thoughts also of Mr. Grossi, who visited us in November 20, I think, in every case in the middle of Corona time, as you see, and we were happily adopting his term that Posiva's onkalo is a game changer. Posiva Solutions, which I mentioned in the beginning, is providing its clients holistic approach to final disposal projects. So we are working in 15 countries at the moment. If you think start from the right, the high level, strategy level, and then everything's related to site selection and monitoring, characterization, then design and engineering of the EBS barrier system, repository machinery, above ground facilities like encapsulation plant. And of course, safety case and safety assessments are an overarching topic. And as we have already all contracts in place and construction finished for the time being, we really know what this costs. So we are assisting other organizations in their cost estimation methodologies, etc. And the uppermost part is the most difficult part, is the stakeholder engagement and public acceptance. We are aware that we cannot copy paste anything that was done in different country in different time. We cannot copy paste to anywhere, but some fundamentals we have obviously been doing right, and this is also an area where we are consulting our clients. So this was my part from the presentation. Thank you for your attention, and I give the floor to Sanna now.
Thank you. Good morning also from Rauma region. My name is Sanna Mustonen, and I act as Safeguards Officer of Posiva, as was here said earlier on. Here is my presentation goes a little bit more further or just into these safeguards topics. And here is the slide having the content of my presentation. First, there are some introduction slides, some few things about transfers of the material, although they already gained something already in Mika's presentation. And lastly, there will be some specific, some slides about specific requirements related to our disposal. Here first, some definitions from the safeguards and non-proliferation. safeguarding nuclear materials, there are, you could say, three aims in that. And first is to prevent the proliferation of nuclear weapons, and then the others two are to ensure that nuclear both material and other nuclear products remain in peaceful use, and these facilities and technologies are used only for peaceful purposes. For that, there is nuclear material regulation, or material regulation is based on the international treaty called Non-Proliferation of Nuclear Weapons, NPT. And Finland was one of the first countries to sign the safeguards agreement with IAEA already in 1971. Then when we joined the European Union in 1995, it was also, there is a need to have an agreement between European Union's non-nuclear weapon member states. And so we have also a contract with that. We don't operate direct with IAEA. There is our Finnish Radiation and Nuclear Safety Authority, STUK, between there, because the IAEA's agreement is between the states. And with STUK, we then develop our national nuclear material regulation systems. And here in the corner of the slide, you can see the world map showing the countries that have now signed the NPT treaty. The development of the nuclear material safeguards in Finland has been ongoing already for a long time. Since the starting of the construction of the Onkalo facility, where what Mika already told you, as that started already in 2003, so Posiva and Finland as a nation has already national and international reporting and noticing obligations. And both STUK, IAEA and Euratom do carry their design information, so-called DIV work in Posiva site already, even though that we don't have any nuclear material yet in our site. During these almost 20 years now, we have developed this disposal safeguards concept for the underground facilities, because as we are the first ones in the world, this has been new for IAEA as well, and European Commission and STUK, how to do the safeguarding. There has been a few points like noticed, like transfer roads and storage locations of the transport casks that are important to surveil fuel assemblies, and disposal canisters are then continuously monitored when they are put underground. And also there are now plans that new kinds of safeguards equipments that have not been used in Finland or elsewhere before are going to be used in our repository. And we have at this point a very strong and lively discussion ongoing about the operator declarations during the disposal operations. And actually at this point in this week, IAEA is installing the first equipment to the encapsulation plant. So these plants are turning into reality. In this slide, there is this whole process of final disposal. In the upper corner, you can see these different kinds of methods are described in this one box, and numbers from 1 to 3 are the different process steps. So the process of final disposal starts from the spent fuel storage at the nuclear power plant. That means that the spent nuclear fuel is owned by the operators, the reactor operators, until they go outside this building. After that, they are in Posiva's responsibility. And here in the corner, you can see that there are these possible ways of safeguards methodology that is designed to be used in the spent fuel storages. Fuel is transported, as shown also in the earlier presentation, inside the transportation casks. And these are normal casks which are used elsewhere as well, nothing special in those. When the transportation enters the encapsulation plant, the fuel is taken from the transport casks and it is put into the final disposal canisters. And now these, as Mika has already explained, the encapsulation facility is ready as a building, and these works are ongoing now inside to install all the machinery. And also the surveillance cameras and so on, what will be there. This part is quite, how would I say, easy in that sense that IAEA has done surveillance in the reactors already for many decades. So that is very easy to design how to put there the cameras and seals and possible laser curtains and so on, because that's quite similar as the other facilities around the world. But when we go down to the spent fuel repository, this number 4, the situation is different. And there are some new methods, for example, these seismic monitoring system designed to be used to fulfill all the surveillance needs. Here is a picture showing the transport cask. As you see, it's going to be, and it is already what we have here in our island. So normal transport cask, where the fuel assemblies are put in. Here in the most, in this right corner, you can see 3 different disposal canisters. And these are different. We are going to use these 3 different designs because we have 3 different sizes of fuel assemblies. And the outer diameter of these canisters are the same, but the cast iron insert is then different, and that's made for each fuel assembly. There are some special requirements related to the disposal. And here is the text, this guide D1, and it just means the name there that it's our national guide. This Finnish national guide is built so that all the IAEA's requirements are already written there in these our national nuclear guides. So when we follow these guides in our design and in our operation, we know that we will follow the IAEA's regulations as well. Here I pointed out some of the special requirements. And the life cycle, for example, in our facility is going to be over 100 years. That has some special requirements for the design. And the other thing is that when the nuclear material is put into the canister and disposal in the facility, you cannot go and verify it anymore because it's put in the capsule. It has overburden of the bentonite material, and even the tunnel is then sealed with a plug. So in the reactor sites, you can always go, if you have uncertainties, you can go and check are there those fuel assemblies or not, what you are requiring. But that cannot be done anymore once the final disposal is done. There's operator shall give consideration to ensure efficient coordination of the safety, nuclear security arrangement, and nuclear safeguard measures. And there is a need for, in the design phase already in the design phase, in construction, and of course in the operating phase, that all these knowledge of the facility is stored properly. As the spent nuclear fuel is traveling inside this Olkiluoto Island, even from Fortum's facility into Olkiluoto facility, the very important thing is the continuity of the knowledge that is assured in every stage, also after the disposal. And it's not just we have to inform our regulatory body not only from the nuclear material movements, but we also need to inform them, for example, our final disposal construction, normal tunnel construction work, so that the regulatory body can be sure that no, for example, extra cavities or extra tunnels are made into the facility. Also, we need to show our designs in advance so that the regulatory body can come and check against our designs that we are really constructing those tunnels what we are supposed to do. And for the continuity of the knowledge, every fuel item and disposal canister need to be uniquely identified. And that's as not only the nuclear fuel is something that you need to know where it is, but the data with the fuel has to be known that it's there where it should be and available when needed. And last, here it is said that the operator shall design the nuclear phase facility and its operation in such a way that the continuity of control data after the verification of the fuel items can be assured every step of the way. So the continuity of the knowledge is very important. How do we then answer into these requirements? First, there is said this handbook. So all necessary provisions for nuclear safeguards when designing, constructing and operating a nuclear phase facility should be somehow identified in our handbook. We have different kinds of handbooks for starting from the design and the construction, and also we have a safeguards handbook. Then about the non-known undeclared activities, how we say to the authorities that the excavation is ongoing only in those places what there should be. So, for example, microseismic monitoring is used for, now I have to take this one back. Microseismic monitoring is used for that purpose. So we have microseismic stations, the same kind of stations that are used for monitoring the earthquakes. We have the same things, but our so-called earthquake excavation is of course very smaller, much smaller in magnitude. And here you can see a picture about our final disposal facility looking sideways from it to the underground. So there are these balls represent a blasting round underground. So when we send this map to our authorities, they can see that, okay, there are, for example, done excavations in the connection tunnels to the canister shafts. And for example, down there is the technical area that has been excavated. And then they can look that against the plans that we have provided them, that do they match. The second one that how the authorities are going to check that on the design or are the constructed tunnels what there should be is the laser scanning, and that this is the laser scanning that is done by the authorities. And here is a picture. First picture shows there in the corner, it's a almost handheld machine device that it's brought into the underground facilities. There is a parking tunnel where this measurement is now taking part in, and in the lower picture there is then a picture about how the laser scanning looks like after it is being done. Third one here is about the ID marking. So the fuel assemblies and the disposal canisters, they have to have a visual readable ID marking. And the fuel assemblies, as normal, they have their own numbers in their handles. That's very common as usual. And also the disposal canisters will have an identification marking. So the marking will be engraved to the lid of the canister. And here are set this possible places where the engraved ID will be then. And the last one is to verify the nuclear material. So that is for that reason also that when the material is given from the reactor owners to Posiva's courtesy, then it needs to be verified that it's exactly the same material that, for example, TVO gives to us that we receive it. And there is that is planned to do with so-called passive gamma emission tomography measurement. And that's the measurement so-called PJET that is being developed during these more than 10 years of final disposal with the authorities. And the detection level is, so as you can see from these pictures, so these are the cross sections from the fuel assemblies that you can even see in the pin level that what there is inside of these rods. So if there is missing pins or something, so that will be visible with these measurements. Oh, sorry, I just pushed wrong button. So thank you. That was my presentation about the safeguards of our final disposal facility.
Thank you, Mika. Thank you, Sanna. If you have questions, go ahead and type those in now. And while questions are coming in, we'll take a quick look at the upcoming webinars that we have on schedule. In March, Advanced Reactor Safeguards Materials Accountancy Challenges. April, overview of nuclear graphite R&D in support of advanced reactors. And in May, graphite molten salt interactions. So I see several questions that have come in. If you should have the ability to, Sana and Mika, to follow along. If you undock the questions pane, I'm just going to start at the top. What is the sound draw? Oh, I do apologize about the sound. It is very difficult, if you can imagine, for technology to coordinate everything internationally. I'm located in Utah. Patricia's in the state of Washington. Our presenters are in Finland. We have time zone challenges. So, you know, bear with us. I apologize. What is the reason for the staged approach for the excavation of the tunnels?
Maybe I can take that. It's two main reasons. One reason is, of course, that related to safety, that if you create, or we try to keep the hollow space underground or in the rock minimized all the time. The greater the space which is hollow, at the same time, the greater the chance that it changes the rock environment. And second reason is cash flow reason. If we are operating for 100 years, so we don't have there is no point of digging 50-60 kilometers of tunnel, which we then need. Part of it we need after 100 years.
Thank you. Did you have anything to add, Sana, or does that cover that?
No, that is a perfect answer, I think.
Great. There's not a question, but a comment. I'm glad to see that maintaining retrievability of spent fuel placed in disposal is a priority. What drove the decision to use iron or copper encasements rather than steel alloy encasements in the canisters?
I can maybe on a general level answer to that, although I'm not an expert. The result of our concept is, or our concept is a result of decades of development and study, much of it done together with SKB from Sweden, who have a similar concept. So all the scientific facts I don't know behind that, but the one main thing is for using copper is that crystalline rock contains water, and that's a corrosive environment. We surround the canisters by bentonite, and that prevents the water from being in contact with the canister. But if, because we have gone through all the ifs, if the water gets in contact with some of the canisters, to 5 centimeters of copper are securing the content from corrosion. And the cast iron insert is bringing the mechanical strength. But I would like to refer to Posiva's website, where we have over 2,200 reports published, and there are several of this canister development for more information.
Thank you. When can you finish the safeguards management report to IEA? At the time of disposal facility closure?
I may answer that. So we don't do, in that sense, kind of a one report, but we are reporting all over the way when we are in our process. So we have certain things that we have to report to authorities yearly, and some things even monthly, and some things that when in our process there are certain process steps, then we have to inform that, okay, we are now in this step and can we continue, and are these all the paperwork, so to speak, clear that we have informed all the possible things. So if that answers the question.
Thank you. There's a question about the retrievability requirement. How do you intend to fulfill that requirement in real time during operation as well as the post-operational stages? Do you want to talk a little bit more about that, or?
Yeah, I can shortly comment that retrievability is reached by, or it has a few things which it has to fulfill. First of all, it must not be easy or cheap for obvious reasons, and the second is that if there would be retrieving, it must not affect the overall safety, or it must not affect the safety negatively. And these are the basis for designing the canister and the tunnels and the whole system, so that the canisters can be mined back safely. This has been tested in full scale with our sister organization in Sweden. So that's a design question. Not easy, not cheap, but possible without affecting the overall safety negatively.
Thank you. Are the canisters for encapsulation designed locally from original defined specifications, or is it adopted technology from an existing design?
That is Posiva and SKB design. The design, the manufacturing methodology, the material, the welding, everything is our own design and own a result of own research and development.
Thank you. Has the IAEA published its requirements for safeguards verification for SF repositories, or is Posiva being used as a test case for IAEA to learn about what is possible for the safeguards in repositories?
Yes, we are a little bit like a laboratory rats in this case. So because being the first ones in the world, so there is not general or specific requirements for verifications yet, and this is ongoing discussion now, that what is enough and what should be now used in Onkalo facility.
Thank you. I'm reminded of the slide in Mika's presentation about stakeholders and the great number of them, and I think that would put IAEA and Posiva on that same relationship.
That is true. So as well that the world is looking for us, it is looking for the regulators as well.
Yep. What dose rates are associated with the disposal canisters in the underground transport, and then once they're in place? Is there an underground transport cast that is used until the waste is finally in place?
Okay, sorry, I just got this now. I just have to read it. Dose rates for people are 0, because everything is automatic and remote controlled. So that is the short question. And so there are no manual work, no men, no staff, so that they could get the dose. And then second one, we don't use any underground transport cask, but the canisters, when they are packed, they are ready for final disposal. So they are lowered via the shaft as such, and they are transported underground as such as they are.
And in underground facility where there is the machine which moves them, they have a shield in the machine, but that's not a whole cask.
Thank you. What is the groundwater table at the site?
Sanna can maybe answer to that,
Yeah.
but it's yeah.
It is. We are we are diving in on our groundwater, so we are in the island, and we are very low island, so we are, more to speak, covered with the groundwater. But that's just now technically we keep the groundwater out from our tunnels.
And then the next question, I believe, is in relation to that. It asks, what is the barrier used in the repository?
The multiple barriers, and the first is the cast iron insert, or in fact the fuel pellet cover, and then the cast iron insert, then the copper canister, and then the bentonite around that, and then the bentonite backfilling of the tunnel. And then of course natural barrier. These are engineered barrier, but natural barrier is then 420 meters of very stable bedrock.
Thank you. I think that addresses the next question as well. The backfilling materials, you've indicated the bentonite.
And the sea area there, sea is in no contact of the final disposal. So this is very good to think about this, so that the canisters are isolated from biosphere, so they will not be in contact with the rock, with the water content in the rock and the seawater. In no case. Sea is in the area 10 meters deep, and we are in the depth of 420 meters and totally isolated from biosphere. And we have evaluated migration of nuclides in the worst cases, and all those results are reported in our reports, and they do not go even in the worst imaginable or unimaginable case. They don't go even close to any borders set for impacts, or limits set for impacts.
Thank you. And I think that addressed that. I touched on the next question too. You've talked about remote work. Can you talk about expected radiation exposure to any workers?
So maybe I can answer into that there are, like said, the remote work is done so much remotely as possible. And of course, when the canister is exposed and on the surface, you don't go near it. Then there is radiation for sure, and of course, and in some cases where you might need to be perhaps near the canister, might be some cleaning works or some malfunction of some machines, but they are so thought to be so unlikely that the doses are very, very low.
Yeah, I could fulfill here that, of course, like every country, we do have radiation limits in the legislation, for nuclear workers and for radiation workers in hospitals or X-ray workers, etc. So these doses caused by any of our activities or our nuclear power plant activities, they are very, very far from those limits always.
Thank you. Can you talk a little bit more about the gamma emission tomography examples that were shown? Only possible while fuel is outside of the geological repository, or is there a means of performing this tomography after the fuel capsule has been placed in its cell or resting place?
Yes, it is so that it's only possible to do these PJET measurements when it's outside the geological repository. So, for example, in a pool area, because that's the device that it goes, or which way you say it, the fuel assembly goes inside to this measuring device. So after it is the fuel rod or fuel assemblies are put into the canister, then they are not, it's not able to measure those with this tomography, emission tomography measurement device.
Thank you. Excuse me, do you consider humidity and salinity of the repository? Are there any plans to prevent potential corrosion?
Just a second, I think there was one question missed. This was about this optimization. I can tell about the optimization, that because now I'm a little bit trying to roll these questions on my own screen. Sorry. Has the underground footprint of the repository been ever subject to optimization? Yes, everything has been subject to continuous and iterative optimization. For example, the volume and the footprint, because every cubic meter of excavation and every cubic meters of backfilling, it costs money. So everything is, I would dare to say, quite often optimized and iteratively. And now I see question of, sorry Berta, what was now the question?
Do you consider humidity and salinity of the repository? And what can you talk about the plans to prevent potential corrosion?
Yes, these are the central factors in our surroundings, in our environment, inside the rock, and potential corrosion is not taking place after the canisters have been surrounded by bentonite, because they are not touching, they are not in touch with water. But if there would be contact with water, then 5 centimeters of copper is enough for hundreds of thousands. No, it's million years at least, enough for corrosion impact. Do you, Sanna, want to complement?
Thank you.
No, I think that's the design basis is that we need to take these in account.
Thank you. How long does safeguards duty continue? Forever?
Well, a little bit less than forever, but long, I would say. It's as long that we have do the operation, then we have to need to do our safeguards duties. And I suppose that when we do the closure, then we have to finalize what are then required for the closure phase. But then after that, then we don't have to do any safeguard measures after that, as is thought now at this point.
Thank you. I don't see more questions. There are people offering thanks and accolades, so I appreciate that. Again, I do appreciate you sharing your expertise, both Mika and Sanna, And Sana, for you jumping in at the last minute, we had a change in presenter very shortly before this date for the live webinar. So thank you for picking up that mantle and such short time period.
Thank you. It has been a pleasure being able to participate.
Thank you, everybody. Thank you for your attention. And please visit Posiva website, Posiva YouTube, and Posiva LinkedIn, so you will find lots more information.
Great, thank you. Patricia,
Thank
do
you
you
very
have
much. Thank you very much, Mika and Sana. As always, the Q&A is so interesting. Thank you again.
Thank you. Bye-bye.
Bye, everyone. Bye.
Bye-bye.
Bye.